Welcome to Chapter 6, Section 2 on the standard normal distribution. The key concept in this section is we're going to talk about the standard normal distribution, which has three important properties. First, its graph is bell-shaped, meaning that it starts with the frequency low, increases to a maximum, and then comes down the other side to another low. Its mean is always equal to 0, and its standard deviation is always equal to 1. And in this section, we're going to learn the skills to find areas, and those areas are going to correspond to probabilities, which can also be turned into relative frequencies or percentages, corresponding to various regions under the graph of the standard normal distribution, so this bell-shaped curve. And we're going to use z-scores that correspond to that area. So first thing to talk about is what's known as a uniform distribution, which we're not going to talk about in a lot of depth, but we'll introduce briefly. So a continuous random variable has a uniform distribution if its values are spread evenly over the range of probabilities. The graph of a uniform distribution usually looks like a rectangle. Although the slides here do not show you an example of this, just understand that that's what a uniform distribution is. Something that we do need to talk about is what we call a density curve. And all a density curve really is the graph of a continuous probability distribution. So something like your bell-shaped curve. That curve is the density curve. And each density curve has to satisfy some different properties. The total area under the curve must be equal to 1. And that should make sense to us based on other things that we've seen in the course, where all probability must add to 1. Probability of success plus the probability of failure, probability of an event plus its complement must equal 1. And that 1 is really the same thing as 100%. So saying that the total area under the curve must represent 1 or 100% of the total probability. And every point on the curve must have a vertical height that's 0 or greater. That is, the curve can't fall below the x-axis. And so what I mean by that is that wherever your x-axis is, the curve is always above that. It never dips below. So there is a relationship that we can establish between area and probability. Because the total area under the curve is equal to 1, and because all probability, when you add the probability plus its complement, or the probability of success plus failure is also equal to 1, there's a correspondence between area and probability that we can use to solve problems. So for example here, we're going to use the area to find a probability. So this is actually what a uniform distribution looks like. We introduced that a couple of slides ago, and I told you that it looks like a rectangle, so you can see kind of what that looks like here. So along this, the x-axis, you have your voltage, and along the y-axis, you have your probability. And so basically what they're trying to show you is that this shaded portion is equal to an area. The area of 0.5 times 0.5, or 0.25. And as we're going to see, we can use an easier way to even find that area using something called z-scores, which we're going to see momentarily. So here's an example of what that standard normal distribution looks like. So again, it's a bell-shaped curve. It starts low, increases to a maximum, and then comes down the other side to another low frequency. The area under the curve is equal to 1. Your mean, which is in the center here, is equal to 0, and your standard deviation is equal to 1. So you can imagine you can go 1 standard deviation, 2 standard deviation, 3 standard deviations in this direction, and you can do the same in the other direction, 1, 2, and 3. Okay, so when finding probabilities using z-scores, for the most part, you're going to use a table to do this. And I'm going to show you an example of what this table looks like in a moment. But keep in mind that z-score tables are standard values, meaning that if you Google z-score table, and you'll get results from that, you'll see that the results that you would get there are the same as what your text would present because they're standard values. So please do either in the text or through a download of a z-score table that I've put into Canvas, or by Googling it, please do find yourself a z-score table because you're going to need it to solve problems here in Chapter 6. And generally speaking, when using z-scores, people use technology to help solve these problems, similar to what we've seen in other sections. May use Excel, or even some graphing calculators are able to compute z-scores. Although we're going to learn the old school way of using the table, understand that technology is also something that's used here. So I'm not going to spend a lot of time on this. I would rather show you the actual table itself. This is just some different pieces for how to do it in using technology. So if you're someone who wants to understand this table gives you an idea of how to use it in StatDisk, Minitab, and Excel, all of which are common statistic platforms, as well as in TI-83 or 84 graphic calculators. There's also a way to do this. So if that's of interest to you, please dive further into this. Otherwise, we're going to move on. So this is an example of what a z-score table looks like. And here in the slides, it only shows us a little snippet. So let me introduce a couple of things about a z-score table. First thing, z-score tables have two sides. One is a positive side, meaning that your z-score is greater than, or is a positive number. And the other is the negative side, meaning that your z-score is a negative number. And the z-scores, you'll see, the way that they're read is z-scores are always 3-digit numbers. It's a number, a decimal place, and then 2 digits. So your first number and your first decimal place will be here along the left and headed down. And along the top will be your hundredths. So this is your tenths place. And along the top here will be your hundredths place. So, for instance, you would read negative 3.45 as negative 3.4. Then we'd come over to negative 3.45. So again, your hundredths digit is up here. And we'd see what corresponds in the center. And what corresponds in the center will be our area, which is also our probability, as we're going to see. And this works both on the positive and negative side of the table. And another thing I'd like to point out before we move any further is when you get a value like this 0.0003 that we got for a z-score of negative 3.45, that is always going to correspond to the area to the left when you graph this out. And as we're going to see, making yourself a little graph in this section is actually very helpful to being able to solve these problems effectively. So, a couple of things about using the table or the z-score table. It's only designed to work for standard normal distributions, which by definition have a mean of 0 and a standard deviation of 1. As we'll see in section 6.3, there's a way to deal with situations where you don't have a mean of 0 or a standard deviation of 1. But for the purposes of section 6.2, understand that this table only works for standard normal distribution. Again, as I already said, it's on 2 pages, with one page for negative scores and the other for positive z-scores. And each value in the body of the table, or the center of the table, is a cumulative area from the left up to a vertical boundary above a specific z-score. And that'll make a little more sense when we actually see this laid out, but just trust me that when I say that it's always the area to the left that it's reporting for you. So when working with a graph, avoid confusion between z-scores and areas. Z-scores give you areas. They are not areas. So a z-score is actually a distance along your x-axis, and your area is a region under your curve. And again, just to reiterate point 5 here, the part of the z-score denoting the hundredths place, which is 2 decimal places out, is found across the top of the table. Okay, so let's dive into an example and see if we can make some sense of how we actually apply z-scores. So a bone mineral density test can be helpful in identifying the presence of osteoporosis. The result of the test is commonly measured as a z-score. So this means that it's not just for the purposes of this course, but when a doctor actually gets a result from an osteoporosis test, they're going to get it as a z-score. And that z-score will have a normal distribution with a mean of 0 and a standard deviation of 1, meaning that we can use our z-score table by definition. So in this problem, a randomly selected adult undergoes a bone density test. We want to find the probability, or the area under the curve, because those are the same thing, that the result is a reading less than 1.27. So that 1.27 is actually our z-score, and we're going to use that z-score and our table to find the probability or the area that corresponds. So first things first, aside from all the numbers that are on here, let's just focus on the basics first, and then we'll dive into what this chart is telling us. I recommend for these problems drawing yourself a basic curve. Give yourself an x-axis, put on your curve, put your 0 in place because your mean will always be 0 and always be in the center. And then place your z-score where it belongs because it was given to us in the problem as 1.27 along the axis. So 1.27 is greater than 0, so we put it over here. Now we're going to actually consult the table. Now here in the slides, it doesn't actually bring up the table for us, but if you grab a z-score table and you go to the positive side of the table, because our z is a positive number, and find 1.2 along the left side of the table and 0.7 across the top and find where they meet, you'll find that they meet at 0.8980. And that is our area, this area under the curve, which is also our probability, which is why it's expressed in a decimal, just like we've seen with other probability. You could also, if you wanted to turn this into a percentage, so you would just multiply this 0.8980 by 100, which would tell us that it would actually turn that into a relative frequency for us, which is the way that we talk about probability in the form of a percentage, which would be 89.8%. Okay. Oh, actually, they do show us the table. Okay, here we go. So 1.2 along the left here, and we move across to 0.7 and find where they meet. So there's our 0.8980 that we use back here to find our area. And again, it's always the value to the left. And that is what we were looking for in this example, was the area to the left, a result with a z less than 1.27. So we've actually been able to solve this problem. Okay, so the probability, based on the results we found, of a random adult having a bone density score less than 1.27 is 0.8980, or if we turn it into a percentage, 89.8%. So now that we've solved that part of the example, one of the things that we need to deal with is what happens when, instead of looking for the left-hand side, like we were here, where we want the left-hand side, where we're actually looking for the right-hand side. And please ignore the numbers for the moment. We'll dive into those momentarily. And so there's a small adjustment that we need to make when that happens. And so we're going to go through this example that's going to show us how to solve when we only know the left-hand side to be able to solve for the right-hand side. And it's going to use that principle that the area under the curve is equal to 1, and that if you know one side, you can subtract it from 1 to get your other side. So this is really a continued example from the previous one. So using the same bone density test, which again, the results will be reported as a z-score, we're going to find the probability that a randomly selected person has a result above -1. Which is considered to be the normal range of bone density readings. Okay, so again, ignoring the numbers, you would draw your x-axis along the end. You're going to put your curve. I would actually put your 0 in, which is where your mean is located, but they didn't happen to do that here. And then I'd put in my z. So if my mean, which is 0, is right about here, this is where -1 would be. So I'm going to use the z-score table to look up -1.00 on the table. And when I do that, I'm going to find that the corresponding area, and this will be on the negative side of the table, is 0.1587. Now, as we discussed, because the total area under the curve must equal 1, if you know a part of the curve, this left-hand side, this 0.1587, if we subtract that from 1, we're able to get our other side. So in this case, our values that are greater than -1. So that would be 0.8413 or 84.13%. So the probability of a randomly selected adult having a bone density test above -1 is 0.8413 or 84.13%. Okay, now Now that we've learned how to get both sides, so we know how to solve for the left, we can take that right off the z-score table, and we know how to solve for the right, meaning where we would take our left-hand value and subtract that from 1 to solve for our right-hand side. What happens when we want to find an area that's between two values? So here's an example. A bone density reading between -1 and -2.5 indicates the subject has osteopenia. And osteopenia, I believe, is a precursor for osteoporosis. So we want to find the probability. We want to find the probability that the area to the left of this z is -2.5, and that there's another z at -1. Now they put this all on one graph, or in two graphs here, but before we continue, let's back up a little bit. So really what you're dealing with here are two different z's with two different areas. And when you find both of them, you're able to solve for the area in between. So let's start with first here. So the area to the left of a z-score of -2.5, which would look like this, this would be on the negative side of our z-score table, is going to be 0.0062. Now, for our second z-score, which is -1, that's a little further up if you put them on the same graph like they have over here, but for now we'll leave them on separate graphs. You would find that the corresponding area to that is 0.1587. And so what you do is you subtract from your larger area, your smaller area, and then that will give you the in-between. So in this case, the area between -1 and -2.5 is 0.1525, which is the difference between the area that we found for our z of -1 and our area that we found for our z of -2.5. Okay, a couple of quick notations to point out. This notation here is read as the probability of having a z-score between A and B. This would be the probability that your z-score is greater than A, and this would be the probability that your z-score is less than A. So just some notation that you might see in equations and in my math lab. Okay, now, what we've learned up to this point is how to use z-scores to find area or probability, which is the same thing. But the table can actually work the other way. If you know the area or the probability, you can find that in the center of your z-score table and use it to back into a z-score. So in this case, they talk a little bit about how to go about doing this, but I'd like to kind of just jump into things a little bit more. So, well, they don't really give you a good slide here. So let me back up a few slides and show you here. So let's imagine that we have an area that's given to us in the problem as 0.5948. Well, if we know that area or probability, those being the same thing, we can see what z-score corresponds. So if I go all the way to the left, I see it's 0.2. And if I go above, it's 0.04. So this area or probability of 0.5948 corresponds to a z-score of 0.24. And so we can use the table both ways. We can if we know a z, like we did here, we can find a corresponding area. And if we know a corresponding area, we can find the z. Okay, let's back up to where we were. Okay, so here's an example of going the other way. So if we were given an area of 0.95, we want to find the z that corresponds with this area. Now, one thing to note is that this is the area to the left. So if this is our z, and we're looking for this area this way, this 0.95 is that area to the left. So when we look it up on our z-score table, we know that we'll actually be getting the number that we're really looking for. So when we look up 0.95 on our z-score table, the closest value that we'll find is 1.64 or 1.65. And so what they've done here is they've kind of split the difference, and they're calling that z 1.645. Okay, So let's do an example where we're going to use known areas to then solve for z-scores. So using the same bone density test, we want to find the bone density scores that separate the bottom 2.5% and find the score that separates the top 2.5%. Okay, now first things first, don't let the percentages trick you or make you nervous. All those percentages are just probabilities. They're just probabilities, but they've been turned into percentages. All right, so what we're going to do here is if we divide this 2.5% by 100 to turn it back into a decimal, we'll find that the area or the probability, same thing, is 0.025. And that will be the same on either side. Now, given that the table reads to the left, it's actually going to be easier to find this z-score than it is to find this one. So we'll start over here. So when we look up on the negative side of our z-score table, 0.025 in the center of our table, so it's an area or a probability, we're going to find that that corresponds to a z-score of negative 1.96. Now, because this is a symmetrical graph, and because the table works symmetrically, if you're able to find one of your z-scores, such as negative 1.96, if you change the sign to be positive, that's actually your other z-score, as long as what they're asking you is symmetrical. So in this case, our two z-scores are negative 1.96 and 1.96. You can also find this z-score one other way, if you wanted to do it the long way. You'll get the same answer, but this z-score also corresponds let's back up. We talked about how the area under the curve is equal to 1. So if we take this little area that is to the right of our z, and we subtract that from 1, we would find that the remaining area, so everything from this z all the way this way, is 0.975. And when we look up 0.975 in the center of our table as our area or our probability, we would find that that would correspond to a z of 1.96. So either way, you'll get the same answer. But just know that as long as it's symmetric, you can just change the sign. Okay. Couple of other things. For a standard normal distribution, you can talk about something called a critical value. And a critical value is a z-score separating unlikely values from those that are likely to occur. And this is a little bit of what the notation looks like. So the expression z with a symbol, this symbol here, denotes a z-score with an area of that same amount to its right. So let's take a look at what that means. Okay, so what we have here is we want to find the value of z with this particular notation. And this notation here is actually meant to represent the area to the right that we're looking for. So in this case, so this is actually the same, asking us for the same thing that we saw right here, looking for this area right here. But this is just another way to note it. So what we would do in this case is we would know that this is our area to the right. So we would need to subtract that from 1 to get 0.975 to then use that number in our z-score table, in the center of our table. And we'd find that that corresponds, again, just like it did in the previous example, to a z-score of 1.96. So this is just another way to write it. But I think it's a little more clear when you actually put it on a graph. But nonetheless, this is an acceptable way to do this as well. Okay, and that is the end of this section. Up next, section 6.3.